Hey, Chem friends, welcome back to day 3 of the new unit on reactions. We're still in 4.1, but today we're going to talk about balancing chemical equations and how to do that. But the law of conservation of mass isn't going anywhere, so I'm actually going to reintroduce that idea again. By the time you walk out of here today, I want you to know what the law of conservation of mass is and balance chemical equations. These symbols, we talked about them in the last learning day, and I'm going to pause on them. We're not going to use them in any of the equations that we do at least this week, but S is for solid, L is for liquids. And if you haven't watched that screencast, please go back and watch that screencast. In fact, you should only be watching this if this is your day 3 learning assignment. So what is the law of conservation of mass? Really quickly, it says that matter cannot be created or destroyed. And if it looks like elements are being created or destroyed, well, then it means that the equation isn't balanced. And that's what we're going to talk about today. So if a reaction starts with, say, 5 silvers, then you have to end with 5 atoms of silver. But what if your equation says you start with 1 silver and end with 5 silvers? Well, matter can't be created, which would be happening in that case. So it means that your equation isn't balanced. We're going to need to balance your chemical equation. And we balance chemical equations by adding what are called coefficients, coefficients. Get that in your guided notes. Now, coefficients is a math vocab word, and basically, it's just a number, placed before the variable. So like 5x, 5 is the coefficient. And if you have 5x, what that tells you is that you've got 5 of those x's. It acts like a multiplication. So if you have 5 silvers in silver's AG, we would write it just like that. We wouldn't write it as AG5. We called this right here subscript. And that was back when we were trying to figure out the compounds, which we're not doing. And I'm not really, I don't think it's something I'm going to ask you to do moving forward. We just had a break. I'm not sure, but we are adding coefficients to balance equations. We're not adding subscripts. So yeah, let's look at an equation. The equation that I gave you is H2O becomes H2 and O2. This is a super famous reaction if you start with water. It is possible to break it down into elemental hydrogen and elemental oxygen. You can't do it. If you go swimming and you start drowning, there's no way for you to produce oxygen, but chemically, we can get the oxygen out of water. But if you look at this equation, we're starting with 2 atoms of hydrogen and 1 atom of oxygen. We're ending with 2 atoms of hydrogen, which is good. That's what we started with, but we are ending with 2 atoms of oxygen. You can't start with 1 atom of oxygen and end with 2. That violates the law of conservation of matter. So a lot of people say like, okay, well, why can't I just write it like this, H2O2? Well, H2O2 is not water anymore. In fact, this is hydrogen peroxide. Hydrogen peroxide will kill you if you drink it. If it's strong enough, it will absolutely kill you. Please be careful. Don't drink hydrogen peroxide. H2O and H2O2 are different. So you can't add what are called subscripts. We need to add coefficients. And we'll talk about how to do this in one quick sec. So I did already give you the notes on this, but I just want to make sure it's clear. We can only balance the equations by adding coefficients. So we can add a number right here, we can add a number right here, or we can add a number right there. But what we cannot add are subscripts. So we can't make that H2O2. All we can do is say, well, we have 2 atoms of water, or we have 2 atoms of hydrogen, or we have 2 atoms of oxygen. So let's talk about that on the next slide. When it comes to balancing chemical equations, there's a million different ways to do this. This is the way I do it, and I think it's a good way. But if you find other things on YouTube, you're welcome to follow those guys. As long as you're getting the right answers, I'm happy. So to balance chemical equations, you want to look at the atoms one at a time. So figure out what are in your reactants, what are in your products, what are those different elements, and balance them one at a time. So first, balance the different types of atoms in your guided notes one at a time. I recommend you look for the atoms that only appear on the reactant side once. So sometimes you'll react and hydrogen will be in both terms, or lithium might be in both terms. So you have two reactants and there's hydrogen in both of them. Balance the atoms that appear on one side, or that appear once on each side of the equation. And I'll show you some examples of this so you know what I'm talking about. So first, balance the atoms that appear only once on each side of the equation. Now, I put this optional and I gave it to you in your guided notes, but there's a list of polyatomics on the back of your Braintree periodic table, and we'll see one like this. If there's a polyatomic, you can balance just the polyatomic. It's a little bit harder, and we'll do an example of it later. So just hang on to that. And then lastly, I recommend you balance the H and the oxygen last. And the reason why is for this first right here. Oftentimes hydrogen and oxygen are in both terms. And if that's the case, they're a lot harder to balance. So I really think the best way to do this is once you have this written down, let's try some practice problems. So pause me, get it written down, and we'll do some practice problems together. This is the same equation from before. Water becomes hydrogen gas and oxygen gas. So if I were using those states of matter, which again, I took out specifically, but H2O is a liquid, L, and hydrogen is a gas, so it would be like this. And oxygen is also a gas, so it would look kind of like this. If you see those states of matter, don't let them confuse you. They're just there to tell you what state that substance is in. So I did away with them because we don't need to talk about them. What I have written here is a chart, and the chart tells me the elements that are in the equation. We start with hydrogen and oxygen, and we end with hydrogen and oxygen. You have to start and end with the same element, so this is a good sign. But I want to keep a track of how many hydrogens and how many oxygens I have. This subscript tells me I have 2 hydrogens. And the fact that there's no subscript after oxygen implies that there's 1. On the product side, on the other side of this arrow, I have 2 hydrogens. And I have 2 oxygens because there's a 2 right there. We have violated the law of conservation of mass by creating an oxygen. We started with 1 oxygen, H2O1, and we're ending with 2 oxygens, which is no good. So what this means is that in order for the equation to be balanced, we needed to have started with a second water molecule. Now, earlier in this week and later in today's activity, you're going to do this pictorially. I'll do the next one pictorially, but this first one, we're going to solve using logic and math. But yeah, we'll do the next one with pictures, and all I need you to do is balance the equation in your notes. So by having a 2 here, that means I have 2 water molecules. Every water molecule has 2 hydrogens. So I've got 2 times 2. I've got 4 hydrogen molecules. And I've got 2 oxygen molecules. Because I have 2 water molecules and every water molecule has 1 oxygen, that means I have 2 oxygens, which is a good sign because I'm ending with 2 oxygens. So my oxygens have no longer violated the law of conservation of mass, but my hydrogens have. If you look carefully, we're starting with 4 hydrogens, but we're ending with only 2, which means we've destroyed 2 hydrogens. And that's not possible. What you start with is what you end with. Oops. So what that means is that there has to exist a second molecule of hydrogen. If you have 1 molecule of hydrogen, it has 2 hydrogen atoms. But if you have 2 molecules of hydrogen, then there's 4 hydrogen atoms, which is a good sign because we started with 4 hydrogen atoms. So we've no longer violated the law of conservation of mass in this problem either. So by adding a coefficient of 2 in front of water, 2 in front of hydrogen, and I didn't add a coefficient, which means it's a 1, which you could put, but I typically don't. This equation is balanced. So what's in blue, you're going to add into your guided notes. We'll try one more. I'm going to do it with pictures. I need a little more control, so I drop down my mega desk. Okay. In this example, we're starting with hydrogen gas and fluorine gas, and we're forming hydrofluoric acid. I put the states of matter in here, but in your guided notes, I didn't put them. Remember, that is just telling you what state it is. Okay, so I want to draw a quick little pic. What we're starting with is an H2 molecule, so I just drew H as blue. There's 2 of them, so I'm starting with 2 hydrogen molecules. Oh, wait, and there's a mistake here. That should say F2. Hang on. Fixed it. Okay, so it's F2, which means I just have 2 atoms of fluorine there. And what I'm ending with is a molecule of HF. So I have 1 H and 1 F. Looking at the math or looking pictorially, we can see that we start with 2 blue circles, 2 green circles, and end with just 1 of each, which is bad. It violates the law of conservation of mass. It can't exist like this. According to science and laws, what you start with is what you end with. We have to end with the same amount that we start with. So in order for this to be real, I mean, what just has to be the case is that there must be more of this HF. So I just drew another molecule of it. I mean, it has to be HF, so I drew another blue stuck to another green. And if we're looking carefully, we can see we now have 2 hydrogen molecules and 2 fluorine molecules, 2 green ones, which is good because we're starting with 2 hydrogen, we're ending with 2 hydrogen. We start with 2 fluorine, we end with 2 fluorine. This does not violate the law of conservation of mass anymore, which is critical. But so when we balance the equation, well, we have 1 atom of H2, We have 1 atom of F2, and we have 2 atoms of HF. If the pictures are easier for you, great, because what we're going to do for the rest of today is balance them pictorially. And if you want to use pictures forever, you absolutely can. I think the math is a little bit more straightforward, and so I'm going to do the math on example 3, but try it with pictures. So hang on. This problem is significantly harder, and it's in your guided notes. If you want to draw pictures, go ahead and try it. I'm going to do it using math. So what I've already started to do was I wrote down all of the different elements here: Ag, N, O, Ba, and S. And I'm just going to try to figure out how many of each I have. Well, Ag, there's just one of them because there's no number after it. N, there's just one of them because there's no number after it. And O, there's 3 of them because there's a 3 there. For Ba, I'm starting with 1 Ba, and I'm also starting with 1 sulfur. So remember, we don't typically write the ones, but if you write them, that's fine. And if that helps you keep track, perfect. Now, on the product side, we're ending with 1 barium because there's no number after it. But what we have here is this NO3 group in parentheses. There's 2 of this whole NO3 group. We have 2 of them because of that 2 right there, which means I have 2 N's and I have 6 O's because I have 2 groups of 3. 2 groups of 3. I just drew a quick little sketch. 2 groups of 3 is 6. So the 2 outside like that, you're going to multiply them together. In my other term, I've got Ag2, meaning I have 2 of the Ag, and S1. So I gave you some rules on how to balance these, and I recommend you do H and O last. So I'm going to recommend you do O last. There is no H here. And then otherwise, balancing equations is kind of like solving a puzzle. You just pick one, you try to balance it. So if I look at this Ag, I'm starting with 1 and ending with 2. That can't be right because if we start with 1, we have to end with 1. So I'm going to put a 2 in front of here, which means I have 2 molecules of AgNO3. If I have 2 molecules of AgNO3, then I've got 2 of the Ags. I've got 2 of the N's. And now I have 2 times 3. I've got 2 groups of 3. I have 6 oxygens. So if I had AgNO3, I could write it this way: 1 Ag, 1 N, and 3 O's. But now I've got 2 of them. So let me draw it again. Now I have 2 Ags, 2 N's, and 6 O's. So right, this is a coefficient. You multiply things by the coefficient. And looking at my bookkeeping right here, I started with 2 Ags, I ended with 2 Ags. That's a good sign. That follows the law of conservation of mass. I'm starting with 2 N's, I'm ending with 2 N's, also very important. In terms of my oxygens, balanced. My BAs starting and ending with the same amount, and S also starts with 1, ends with 1. This right here, putting a coefficient of 2 in front of there, balances this chemical equation. So how many BASs do I need? Well, I need 1. I mean, we don't write the 1 typically, but if you want to write it, you're more than welcome to. How many BaNO3 do I need? 1. And how many Ag2S's do I need? 1. Now, if you feel like you have a good sense of this, there's a balancing equations gizmo that I want you to try. If you still need a little bit more help, I'm going to do one more example. It's actually this one. I'm going to do it again. And I want to talk about that polyatomic ion thing. So if you want to stick around for that, that's perfect. If you want to jump ahead into the daily key concept, to balance chemical equations, we add coefficients so that we have the same number of each atom on both sides of the equation. That way matter isn't created or destroyed. Let me pull up the polyatomic sheet for those of you sticking around. This right here is your polyatomic list. It's on the back of the reference sheet. Oh, wait, this is the honors reference sheet. That was the wrong reference sheet. So everyone should have this at this point. I hope everybody has something like this. And if you came from honors, you have the honors one, and both of them have a list of polyatomics. The honors sheet just has more polyatomics. Polyatomics mean multiple poly, atomic meaning atoms. So these are ions that are made up of multiple atoms. Typically, we would have done more with them in the ionic unit, but this is remote learning. When you're balancing equations, I said optional. That third bullet point says optional. Balance the polyatomics if they appear on both sides of the equation as a single unit. So back in this problem, hang on. Back in this problem, we had this NO3 compound right here, and that is a polyatomic. If we go back to our reference sheet, you should be able to find it right here. NO3 is compound nitrate. I mean, I don't know if you're going to want to balance the polyatomics separately because we've never talked about them before, but if you see them, you can treat them as one unit. So I'm going to show you how to do that also. If you choose to balance the polyatomics, it is easier. So if you're watching this, I'm just trying to make your life easier, though it might not seem like it. When we keep track of our elements, we've got Ag, No, Ba, and S. But if we treat NO3 like the polyatomic it is, we can just put it in one box. You can only do this for polyatomics. So I can just stick NO3 together in a box. So N and O came together. When I'm trying to balance this now, I have one Ag, yeah, and I have one NO3. I've got one of that NO3 group. I've got one Ba and one S. On my product side, I have one Ba, but I've got two of this NO3 group. There's just two of the nitrates, two NO3s. I've got two Ags and one S. Balancing this way is usually easier because it's more straightforward to figure out what's wrong. Your Ag is bad and your NO3 is bad. They violate the law of conservation of mass. To make them not violate the law of conservation of mass, we need a second molecule of this. Now we have two Ags and we have two of this NO3 group. So I'm just calling NO3X. So if I start with one, I've got one Ag and one NO3 group. But when I have a two there, it means I have two of this molecule. So I just drew it again. We've got two Ags and I have two of the NO3. Remember, I'm calling NO3X here. This is just a slightly easier way to balance equations. And because we've never talked about polyatomic ions before, I'm not sure if this is something that's going to be interesting or helpful in any way, but I thought I would at least present it to you in case it's something that you think may help. You have that list of polyatomics. You always have that list of polyatomics. And if there's a polyatomic, you can just balance a polyatomic as one substance. But go give it a try. I mean, try the balancing. Do some polyatomics, do some split up, and see what you like more. And let me know. I am actually curious. I'm sure like 95% of everybody has already shut the video. But if you're still watching, then you're one of the few people who care. I mean, not cares is the wrong word, but I was really striving to understand this, and I think that's awesome. So let me know which way worked better for you, and I'll catch you next time. Thanks for watching. Bye, everybody.